Hi, everyone. Thank you so much for joining this webinar today. Hopefully you can all see us and hear us. So we are very excited to welcome Jennifer Groth from our global audiology team here at GN Hearing, and she's going to be able to tell us some really exciting research that's been being worked on over the past probably past year or so, Jenny, and share how what we can do with, especially with our unique GM philosophy, can help your clients to hear through the noise. So before we start, and I hand over to Jenny, I want to give her a proper introduction. So, Jenny is a director of audiology communications and strategic projects in our global audiology team at GN Hearing, and she's based in the US. She has a background in clinical audiology and has filled various roles in research and development and marketing at GN Hearing since 1996. She holds an MA in speech pathology and audiology from the University of Iowa. So we are very lucky to have her. Thank you so much, Jenny. And now I'll hand over to you to take it away.
Okay, thank you. I am just pulling up some material here to share with you. It's super interesting to hear those introductions because I never remember what I told, what information I gave people to say. So now I know. But hello and welcome to everyone. I have to admit, when I was asked to do this webinar, I wondered who in the world would sign up for an hour of some lady talking about environmental classification in hearing aids. But here you all are. So either you are super desperate for continuing education units, or you are just as nerdy as I am about hearing aids, or maybe you would just like some behind the curtain information on how hearing aids are operating to give you some better insight in what you meet in your clinical work. Whatever your reason for being here, thank you so much for joining, and I hope we have an enjoyable hour together. I was going to make a little disclaimer about my expertise, but again, I had forgotten what I told Lisa to say about me. But you heard I'm not a researcher, an engineer in speech or sound recognition technology. My perspective is as a veteran in audiology, and I've been with GN for 28 of those years in back office sort of roles in product development and a little bit in marketing. Currently, a main responsibility of mine is identifying and substantiating and communicating about audiology-related claims. And so I spend a lot of my time poring over hearing aid-related research and giving the third degree to our internal people, researchers and engineers about how things are designed, and also collaborate with my colleagues in our global audiology group to plan and execute in-house and external studies. Our topic, environmental classification. If you look on hearing aid data sheets, I think we list this as a feature. And my first question then would be, what is a feature really? I'm not sure I agree I would call it a feature if I was in charge of data sheets, which I'm not. So I thought I first sat down and tried to make myself a little taxonomy of hearing aid features, admittedly because I wanted to use the word taxonomy, which I think is a cool word. But trying to do this almost broke my brain, so I ended up just informally grouping things that I want to show you. But yeah, now I got to say the word taxonomy, so my day is complete. But hearing aid features, what are hearing aid features? I'm just kind of broadly grouping them instead of trying to organize them hierarchically. And what pops into my mind when someone says hearing aid features are the sound processing features. So these are here's some examples of them. This is not an exhaustive list, but they're ones that modify the sound that's delivered to the ear. And for the most part, they are driven by some kind of audiology rationale, or either that or trying to solve an amplification related side effect like feedback in order for the patient to receive the intended benefit of the other features. We also have what I would call hardware features, which is pretty self-explanatory. It's basically anything you can see or touch or that can break or get earwax in it. And you've probably seen all of that. And then we have functional features which do something that might not directly provide hearing benefit, but that has some other benefit. Convenience is a big one there, like we see with rechargeability and also connectivity, remote care for that matter. And then finally, we get to something that really starts to relate to environmental classification. And those are features that control other features, as I call them here. You could also call them automatics. These are the mysterious things where no one really knows what they're doing, but they turn things off and on and adjust the strength of those things. And finally, I tried to make a distinction between feature and technology. So there are some buzzwords that you're hearing a lot today, like AI. That's not a feature, but a capability that you could use to make a feature with. And I guess actually digital processing capabilities could also fall under hardware, but they're what enables and also limits some other things. I mentioned this technology category because things here may be used a lot in marketing and used to imply superiority that in and of itself doesn't really make any difference to patients at all. So the fact that a hearing aid maybe has some kind of sensor in it other than microphones is pretty irrelevant unless the data picked up by that sensor is used for something that makes a difference to patients. I would kind of want to put environmental classifier in as a technology that is an enabler for other features, for these automatic features. Let's jump over to philosophy, product development philosophy for a second. When we or any other manufacturer are developing a product or feature, that's at least to some degree driven by an overarching philosophy about what we want to accomplish or what we want the hearing aid user to experience. Admittedly, there are some things that get developed because of market demand or for competitive reasons, but overall, there's a lot that tries to follow a high-level ideology about the job of a hearing aid. I copied a sentence from a marketing piece from another hearing aid brand. And it doesn't matter who it is or what they are specifically talking about. But when I read it, I thought about how starkly it contrasts to the philosophy that we follow at GN. So the sentence here, it's the highlighted part that struck me. If the signal contains information the hearer wants to hear, the wearer wants to hear, it will be processed as XYZ, whereas if it contains unwanted or distracting sounds, it will be processed separately as something else. XYZ. So how does the hearing aid know what the wearer wants to hear? That's the thing that really stands out to me. The hearing aid can only guesstimate based on what? Today, hearing aids would be guessing the user's intent based on the analysis of the acoustic environment. In some hearing aids, there are also, for example, motion sensors that might be incorporated to make the guess more accurate, but that's still a guess. The hearing aids they can't know what the wearer wants to hear. At GN, we're not guessing user listening intent because we know we don't have a foolproof way to do that. So we use technologies in a way that support what humans are better at than hearing aids, like knowing what they want to pay attention to. It's using the technology or the machine, if you will, to empower the human. So we're trying to create some synergy here where we leverage the strengths of both, leverage the strengths of the machine and leverage the strengths of what the human or the human brain is good at. The approach that's embedded in the sentence I copied here is the opposite. In this case, it's well-intentioned, but the technology or machine is empowered to help the human based on some assumptions about what's best for the human. So it's not only the technology per se that's important. As important is what the role of the technology should be, and that in turn informs how you implement it in a product. So our way of trying to use technology in a way that that empowers the human, that lets the user be in charge of their listening experience. That's part of what we call organic hearing, which has 3 different pillars, and the only one that I'm going to mention here is one that we call hear naturally, meaning that you use your intuitive listening strategies to when you're wearing the hearing aids to help you hear better, and the technologies that we implement to do that assist you in that, but don't take over from you. So a hearing aid user. First of all, before we go any further, notice I put a gold star on this poor guy's forehead. This is a public service for you. I added stars where there's a related quiz question for the CEUs. And there's 5 of them in this presentation. And then there are 3 additional questions, which are super easy. So you should get those with no problem. But I just want to make you aware when I'm saying something that you're going to be asked about when you do your quiz. So anyway, we have a hearing aid user here, and even though, I promise I'm going to talk about environmental classification in excruciating detail, but I want to set the scene here first with what is a main concern for us at GN, and that's the people who come to see you are, of course, unique individuals, but there's still some things we can safely say they have in common, and that is problems hearing and noise. It's very striking that the biggest need of those with untreated hearing loss and a main driver of satisfaction has to do with hearing and noise and how well your hearing aids are helping you to hear and noise. So we put a lot of focus on that in our hearing aid development, not spending so much time in other spaces looking at how to, for example, incorporate health and fitness things in hearing aids. We're still thinking mostly about hearing health and specifically hearing and noise. And we're depending a lot on environmental classification to help us to do the right things at the right time. And how do we know how much the technology meets this need to hear better in noise? And as I said, there's a big dependency on what I'm calling the engine of the hearing aid here, which is environmental analysis. So in order to answer whether we know we're doing the right thing or not, or whether we think we are, we need to start with what's running the hearing aid's decision-making processes and how they can empower the user. In terms of what causes all the highly marketed features we otherwise talk about to turn off and on, there's a control center in the hearing aid that you can call the environmental classification system. All hearing aids, all modern hearing aids these days have some system some way of gathering data from the listening environment, and that helps them make decisions about when to activate and deactivate things, certain features and operations. And in a way, the environmental classifier is, you could say it's the engine, the motor control center for the hearing aid. The way that any hearing aid brand breaks down the sound environments and what specific information that any company would use to do so is probably different, and it's for sure unknown, or that lovely word we like to use, proprietary. Sounds very fancy, but means we're not going to tell you. But that doesn't stop us from being able to use the tools that are provided, for example, in fitting hearing aids, like in fitting software, to try and answer one critical question about environmental analysis, and that is, how accurate is it? After all, an environmental classification system is responsible for kind of the overall functioning of features and therefore the expected benefit that the user gets from those features. So the very first thing that we need to be sure about is to establish what is the accuracy of how we're breaking things down and analyzing things so that we apply the right things at the right time, so that they conform to what our philosophy is. This is kind of the lowest level of assurance that features will work as they were designed. But what does that mean, accuracy? How can we measure accuracy in an environmental classification system, especially since we don't know what, it's fairly invisible what the hearing aid is doing? Well, one thing that we decided we were going to use as a gold standard was the subjective classification that uses human listeners. So if human listeners agree that they are in a noisy situation or a quiet situation or a speech situation, we think the hearing aid should probably identify the situation the same as human listeners do. So we started out a few years ago to try and test the accuracy of our own system and also other systems on the market by following a few steps, where step one was we started by picking some recorded sound samples that we felt were representative of different listening environments or sounds that listeners would be able to agree on. So to establish our gold standard, I think we picked 10 sound samples and one instance where we would just not play any sound file. And we deliberately picked samples that we thought were very straightforward and people would agree on pretty well. There were some scenes, like at a cafe, a train station, supermarket, things where there were mixed sounds. And then we had other types of sounds in isolation, like I think we had a hand mixer, we had white noise, and we also had some conversation and quiet and some different types of music. So then for step two, we found some naive volunteer listeners there were 9 of them in this first study we did, and they were employees at GN, but not audiologists, not engineers, not trainers, not salespeople, or anyone else who would be at all familiar with the details of the hearing aids or know anything about what terminology to use. And we asked them to describe each sound sample in 3 or 4 words maximum, completely open-ended. And we asked them to make their descriptions very generic. So we thought that they might just naturally come up with the same sorts of descriptors that we thought that our prototypical categories should be called. So, for example, we told them if it was Frank Sinatra singing, that they should just say singing or music or something, and not specifically Frank Sinatra, because that isn't, the hearing aid is probably not going to identify that. We expected that people would mostly say stuff like speech and noise, music, etc. And of course they didn't. Well, they didn't do that, exactly that. There was some good agreement, but also a lot of other words thrown in that made the picture unclear. So, it is very, very systematic approach, but then it doesn't give you as clear results as you thought you would. So luckily, we also included a closed set task or listening task or classifying task. But let me just show you a few things from what we got out of the open-ended results so you can see what I mean. To some extent, this is just a small snippet of what of our results here. I'm not going to show you all of it, but to some extent they did say what we expected. For example, 8 of the 9 people said the hand mixer was noise, but 8 of 9 also said it was loud, which we weren't really anticipating that. And there were a lot of other words used by individuals that didn't necessarily describe the sound. Some of them did, like for the mixer, again, grinding is kind of a sound description. Some of them actually named the sound, like saying it was a mixer, and then some described the experience of listening to that sound, like saying it was irritating. For the supermarket scene, which has a conversation going on against a background of typical supermarket type sounds, including some boring music, at least 8 of the 9 identified the conversation, but then similar to the hand mixer, they used other words that identified other aspects of the scene as well. So we followed that up with closed set task in the subjective classification in case the results were a little muddy, which they were. So we wanted to validate that people would pick the words we already were hoping to use, which were speech, noise, quiet, and music. So in this part, we asked them to pick up to 3 of those words from that closed set that describe the sound sample and see if they were indeed agreed with us that those were good words to describe those scenes. And so this is just a summary of all of the different sounds that we were using and how many of the 9 people agreed. It was much, much clearer that they did agree. There were at least 8 and mostly 9 uses of the same word or 2 words for every sound sample, and then a few scattered use of other words to add more info. So, for example, in the supermarket scenario, there were 7 of 9 people who also added that there was music in that environment as well, but 9 of them agreed that there was both speech and music present. So what we ended up with, or ended up concluding, was that the listeners did agree on how to subjectively classify these sounds, and that we could use them to see if hearing aids agreed with them. So we took all of the samples and the words people picked to describe them and put them into these 5 prototypical environments that are speech and noise, noise, speech, music, and quiet. Then we took hearing aids from all the main hearing aid brands that show some indication of environment in their data logging, and I think there are 4 of them, and put them a pair at a time into a test box. And then we looped each of these sound files for up to 24 hours. For the super easy ones, like not playing any sound, which would correspond to quiet prototype environment, we only did about half of that time. We didn't interleave the sound samples, although that would be interesting, but that would sort of be a different experiment. We did 1 at a time, so there wouldn't be any doubt about how to compare the results or the classification with what the human judgments were. So we tested 1 pair. We didn't have equipment to do these all at the same time, so it took about a week to do 1 hearing aid here. And so you probably think I'm going to show you our results, but surprise, I'm not. Instead, our results are published on Audiology Online from 2017. But the reason I'm not going to show them is because we have a newer study where we did a similar thing, but also because I would like to share with you results from some independent researchers who basically replicated our study, but did a better job with their methods. And where we just put the hearing aids in a test box and played the sounds, they put the hearing aids on a mannequin and played the sounds via a multi-speaker setup in Freefield that kept some of the spatial cues there were in the sound files. So it could have been that in our study, maybe we committed some injustices against other hearing aid brands that this group, Yellen Seti and colleagues in 2020, that they avoided by doing it in the Freefield and recording the response to the hearing aids and then reading out the data logging afterwards. In this, I copied a sentence from their study where they point out why they're interested in trying to assess the accuracy of environmental classification. That's this comprehensive assessment of environmental classification is essential when considering the cost of signal processing errors, the potential impact for typical wearers, and the information available for use by clinicians. The magnitude of differences among devices is remarkable and to be noted. So that's kind of foreshadowing their results. And they also had it, this is also their figure here, where they had a really nice process description of the principles of environmental classification. So from the audio source entering the hearing aid through the microphones, you have, there's one path that's the amplification and the processing, but then we're also using that information or the microphone as a type of sensor and extracting acoustic features from that. And they list a number of those that might be used in trying to classify the sound that's in the environment. And then there will be some sort of model that actually does that. That's the middle part where they write estimation of the feature space and proportions using assumptions and parameters to form interclasses. That sounds very fancy, but basically this is where it gets broken down into the categories. And then after that, there are the decision rules applied on the basis of what's done in the middle there, in that second step. The operation of the hearing aid features based on the manufacturer-specific algorithms, and also hearing aid feature activation, subsequent changes to signal processing to be individual to or beneficial to an individual user. I would also add here that some hearing aid brands, and GN is one of them, also present the hearing aid fitter with a pretty detailed view of the environmental classification breakdown during the use of the hearing aid. So that is meant to be a helpful clinical tool as well. I'm not sure how much people really look at it. I think people look at use time a lot, but we do also show you environmental data if that's something that you want to see. Okay. This, let's take a look at their results, and you need to fasten your seatbelts because they figured out a way to put everything in one graph, and it's kind of insane. I would add that GN hearing aids were not included in their study because they wanted to include hearing aids that classify music. And we're going to talk about that a little bit more in a bit, but let's just start off by showing you their big graph. And I covered up most of this with the gray bars to start with to make you not pass out or go away, make it less overwhelming. And I'll take those off in a minute. But let me just show you to explain how their results graph is set up. Along the top here, they have these categories, and this is the way they broke down the categories. So they had speech and quiet, speech and noise, noise and music, and they had 4 different. Oh, I have a fancy cursor here. Let me take that one out. Is that? No. Okay, never mind. Along this, laser pointer. Sorry, here it is. They had 4 different scenarios that they presented, or that they looped for the hearing aid for each brand of hearing aid. They had a conversation between 2 people. They had a scenario, more complicated scenario of speech and noise at a food court, like a mall. They had some music, and they had also some more music in a card hall background. So where there's a lot of other stuff, I guess people playing cards and talking in the background of that one. There's the one thing that I would point out here about the categories and the names of the categories. There's no finite number or official designation of listening situations. So this is always a decision made by whoever designs a classification system or a study. Oh, where did my bars disappear? Oh, anyway. Let me go back. Okay, we'll just go on here. For whoever designs the classification system, for the evaluation in this experiment, they used recorded sound from very specific listening situations, and they defined very generalized categories that they tried to match up with the hearing aid manufacturer's descriptions of how the sound scenes were classified. So my point here is that anyone who makes up a classification system is doing just that, making it up. In real life, there are an infinite number of listening situations, and there isn't any right or wrong way of doing this or trying to classify them. But for hearing aids, it does make sense to, at a minimum, divide things into speech and not speech, because that's very important for listening. That's typically why people seek hearing aids in the first place. Here they also included music because hearing aid brands they tested in this study included music identification. And whether or not that's desirable is not a bygone conclusion. We'll come back to that in just a bit. So I mentioned here we have the actual sound files, and we have the categories here. And then you'll see there are 1, 2, 3, 4, 5, 6 things along the top here. In this column that says S, that's their human subjective evaluations. And then you see they have different colors. Well, not different colors, it's monochromatic, but it's white to black and their scale is over here, 0 to 100. And that's the proportion of times that that there was agreement that that sound sample fell into that category. And they tested 3 different levels for each sound sample. They did see some differences depending on the presentation level. So in cases where you have like this one, almost a completely white box, there was a lot of agreement that this sound, which was music with no noise, was not this category. So neither the human subjects nor the hearing aids identified music with no noise as noise. There were very small proportion for hearing aid E that did identify that as noise, but mostly there was a lot of agreement that was apparently an easy task for the hearing aids and in agreement with the human subjects. This one, there's some other, anytime you see it, the whole big box has pretty much the same color. That's where there was a lot of agreement between the human subjects and the hearing aids, and they were identifying the same thing. So there was overall, for a 2-person conversation, which you would think would be a very easy environment to identify, overall a lot of agreement, but there were some kind of weird things here, like hearing aid C identified 100% of a 2-person conversation as speech and noise. But it was only when the presentation level was a little louder. So that suggests that this particular hearing aid classification system is really putting a lot of weight on the overall sound input level, so that if it exceeds a certain level, it's going to call it noise, unless it has some other content like music maybe. You can see in the more complicated environments like the speech and noise at a food court, you have more of a checkerboard pattern, and especially when you get down to this music in card hall background, there's a lot of disagreement there on what's going on, and where it's not clear that the hearing aids agree with the human listeners or with each other about what's going on in that situation. So that's a more complex environment. I never heard those sound samples, but just from their description, there was more going on in that environment than with the speech in noise at food court, which probably didn't have any music in the background. Environments that include music, but where music isn't the only sound, are especially tricky. So how will the hearing aid know what to prioritize? Brand B in the music in card hall background classified 90% of the logged hours as music. Where is that here? When the sound level was loud, but not when it was moderate or low in level. And it would follow that this hearing aid is going to have applied settings that are optimized for music when when it's identified so many hours as being music. Would that be the listener's intent in this scene? The listeners themselves were kind of 50-50 as to, so you can't really see these numbers, but these are around 50%. So they were kind of half in agreement as to whether to call this environment music. And that could reflect some differences in what their human listeners imagined that their intent might be in this scenario. It's complex. There's a lot going on. Maybe they're one of the card players and they need to hear what's going on there, or maybe they're just sitting back listening to whatever music was in there. So music identification is pretty fraught if you put it into your automatic steering system or automatic control system in the hearing aids. The authors of this study point out several places how similar their results were to ours, and I copied one sentence here. Across devices, the proportion of speech and noise classification for speech and noise scenes ranged from 38 to 100%, a value strikingly like the 41 to 98% range reported by us at GN. So that's just one example. So when we decided to update our findings with newer hearing aids recently, We decided to use basically the same methodology as in our original study in 2017, rather than making it real complicated, because their results were in such good agreement with ours. And I'll show you those results in just a second. But first I want to change gears a little bit to share with you what's going on under the hood with the environmental classification in our hearing aids. I can give you quite a bit of detail on that, but because hearing aid brands don't typically market or publish how they classify sound environments, I obviously can't tell you what anybody else is doing. The fact that there are these observed differences, though, in these studies, and how the hearing aids react to the same sounds suggests that our methods do differ, and this can translate to the hearing aids behaving differently in the same environment. So both because they're identifying the sound classes differently, and then also because as manufacturers, we're following different rationales and using the features we have in different ways according to a different philosophy. This, in case you don't recognize it, but you probably do, is a spectrogram. Speech detection is the most essential element in the environmental classifier, and that's for hearing aids across the board, not just GN hearing aids. No matter what hearing aid brand you have, the way you want to apply and adjust the features is to some degree going to be to enhance speech or at least avoid degrading speech. So you always will need to know when there is speech. And the most basic way to identify speech, and this is what hearing aids were doing 25 years ago, is just to look at the modulation or the fluctuation of the signal, because for speech it's quite large. It's like around 30 dB if the speech is in quiet. And then the higher that modulation is, that's a proxy for the presence of speech. That is pretty simplistic, and the problem with it is you have a lot of false positives there, because there are lots of sounds, even just like tapping sounds, that have a lot of modulation that can be as big as speech, but that aren't speech. So I think definitely we have, and probably other manufacturers have built on that to have better speech identification systems. If we look at the spectrogram, we can identify what some of those are. So if you're familiar with a spectrogram, you know that there's time along this bottom axis and the frequency from low to high along the vertical axis. And then the color, the darker the color, the more intense or the more energy there is across time in this particular frequency region. So things we can observe here in the spectrogram are, for example, that there's some aperiodic, not very, very intense, and also high frequency sound here. So that's likely some sort of fricative. Then there's a little pause right here until something else happens, and we have some periodicity, some repetition here. So that's going to be a voicing. So this will be a vowel, and you can also recognize that there's energy and patterns here at the formants of the vowel, and that those change as they go into the next speech sound. You can see approximately how long these different, you can identify these as speech sounds and measure how long they are. Finally, at the end, there's again a little pause, and then a quick release of some energy here at the end. So all of those things, the frequency content, the fact that voiced parts of speech tend to be much more intense than the unvoiced parts, like this here, the length of the different speech sounds, those things they create patterns that are recognizable. And that's what we've built into our speech detectors, or what we call our speech detector. So we are checking spectral balance, because speech will have variations of or alternating high frequency and low frequency components, and the low frequency components are going to be more intense because that's where the voice is. We check the signal durations and the pause durations, maximum durations, and we check the repetitions of the high frequencies so that we don't identify any sort of weird clicking sound or anything as speech, because that could also be a false positive. So we combine all those things, and what comes out of that detection system is a probability that there's speech. And then we use that further in the classification system. We also use it for specific control of a lot of features, and I'll mention that toward the end. But for right now, just know that we're using it in the classification system. So once we know where the speech is, we can do, well, we can make our, no, we can't make our, this is weird. I have a picture on this slide, but it's not showing up for you. But we can see if we have a waveform of the signal, it will consist of, and it's a speech signal, someone talking, it will consist of the speech, and it will also consist of whatever noise there happens to be in the background. So the total signal will consist of both the speech and the noise together. If we know where the speech is because we have a good speech detector, we can measure the noise in the parts where there is no speech. The noise spectrum for someone talking in a noise background tends to be fairly stable. So once we know the speech, we know the total signal, and we know the noise, we can estimate a signal to noise ratio. And that is a key component of an environmental classification system. And that's for sure what across manufacturers, what all are trying to do is to make a signal to noise ratio estimate. The signal to noise ratio estimate we use, I'm not going to talk about these other things, but we use it specifically in the environmental classifier. And I'm going to show you right here what a conceptual representation of how our classifier looks. Now, recall I said that it was kind of, yeah, the classification system is something that we make up. There isn't only a certain number of listening environments, and you can choose how you want to classify environments. The way we do that is by focusing on speech and non-speech, or what we would then call noise. And we create the environments based on the signal to noise ratio and the input sound level. So at the bottom there where it says quiet, if the input sound level is under a certain amount, and it doesn't matter what the signal to noise ratio is, we're going to call that quiet. It doesn't matter if there's speech present, we'll call it quiet if it's under a certain level. But once it exceeds a certain level, then we're looking for speech. If it's a very high signal to noise ratio, it's just speech, either at a louder or a little bit more moderate level. If it is mixed in with some noise, if the signal to noise ratio is lower, then it's a speech and noise environment. We have two of those, one that's louder than the other. And by the same token, we have two noise environments, and one is louder than the other. So one thing you might notice is that there's a circle with red color in each category and gray around the edges. That's not just for design. It wouldn't be a very good design anyway. It's not very pretty. But what it's trying to say is that there's a degree of uncertainty when you have environmental classification. The classifier is going to output a set of probabilities that the acoustic environment matches the criteria for the categories. And this, by having these, this gray area is indicating that we're trying to take into account uncertainties when the environment is complex or changing. And the grayish areas in between categories are the lower probabilities of that environment. We're not entirely certain that the environment is correct when it's meeting criteria in the gray areas, and the red areas is when we're very certain that it is that environment. And the reason it's important to capture the gray areas isn't so much for a categorical classification. It's more because when we use the classifier to control a specific feature, then if it's if we're not entirely certain that the environment is exactly what we think it is, or if it's dynamic and changing between different environments, then we can control the environment by combining the probabilities, or making a weighted average based on the probabilities of these environments, and we can steer the feature better to be smooth and not create abrupt transitions that we know will be bothersome to users. So we use that uncertainty to modulate the actions that are applied as a result of the environmental data. So as I mentioned, not all hearing aid brands are going to break down things in the same way or call environments the same thing, which is very inconvenient when you want to study it. So we had mapped to prototype categories in our study, and that's also what the YLM study what they did. Last year, we decided to update our study with the latest premium hearing aids to show environmental data in their data logging, and we used our same test box methodology. But to lower the bar even more, we collapsed our category and make it easier to map what we saw in the other hearing aids fitting software. We collapsed our categories into a smaller number, with the risk that we would wipe out some of the differences between hearing aid brands. So we thought maybe we wouldn't really see much in the way of differences. And that was entirely wrong. So let's take a look at those results. When we broke down our prototypical environments to the most basic in terms of speech presence and noise presence. So we had 3 environments: quiet and speech only, speech and noise presence. That should be super easy for hearing aids to classify correctly, but apparently not, because you see there are some pretty big differences across brands. So the GN are the red ones, that's the quiet environment, but the GN ones are these ones, and then we had 4 other brands who show some sort of data logging that we could look at. And there's quite a lot of variation. The one that was easiest for everybody to categorize correctly was the quiet and speech only, but there is even some variation there, which seems a little weird, because how hard can that be to identify quiet and only speech? That's sort of the very basic job of the classification system. Speech and noise were either equally hard, or speech and noise was very hard for brand A, apparently. Big differences across brands in any case. So this is the same data from the previous slide, but just collapsed per brand to give you an overall impression of accuracy. And the GN is quite high, and the other ones are considerably lower. But why? Why is it so low for the other brands? This was a pretty easy task. We saw that accuracy for speech only and quiet was high across brands. Those are the easiest environments. But noise, and particularly speech and noise environments, were not so high. So one of the things we found that really hit some of the other brands hard was music identification. And it wasn't because we had music samples in our study. We did not have music samples, but you might think I'm talking about that supermarket scene where there's music in the background. And yes, that did contribute a little bit. But the really puzzling finding was kind of an artifact that was in complete disagreement with the subjective evaluation. One of the samples we used in the study was a vacuum cleaner. We hadn't used this one in the 2017 study. We had used a hand mixer, but we found in preparing for this update that listeners also were in unanimous agreement that a vacuum cleaner was noise, and we used it because it was louder than the hand mixer, and we thought that would be a good thing, and easier even for the hearing aid classifiers to identify. But but check this out. So here you only see the other brands that we tested, because we don't have a music identification or music classification in our system, but the other brands do. And here we're looking at the proportion of vacuum cleaning that was logged as music. It was 90% for brand A, and not so bad for brand B, and pretty high for the other two. And while I will be the first one to admit that hearing someone else do the vacuuming is music to my ears, this is not the expected result. As I said, I think this was kind of an artifact of the music identification algorithms, because the vacuuming sound that we used is recording an upright back. And if you've ever used one of those or heard someone using one, you know how it kind of goes up and down in pitch while you're pulling it back and forth. My guess is that pitch change must be what triggered the music category to be chosen, but it's still in complete disagreement with human listeners. One lesson here is that the hearing aids can be doing some odd things now and then based on their environmental analysis. And probably most hearing aid users would prefer some extra noise reduction or maybe even volume reduction in the vacuuming situation. And music settings, if that's clearly what I bet brand A and brand D would be doing most of the time here. They would do exactly the opposite of that, because music settings try to minimize signal modifications. Another lesson is that maybe music identification isn't such a great idea, or at least not for automatically controlling the hearing aid settings. Maybe it's interesting to present that information to the hearing aid fitter so that you can see that the person is in music environments, but not to control the hearing aid settings automatically. There are quite a few environments that have music in the background where you aren't actually interested in the music. There are all kinds of shopping venues that play music to help create some kind of atmosphere, but that doesn't mean you want to actively listen to it. Actually, I had a kind of funny experience the other day where my husband and I were viewing a house for sale, and these people had a bunch of smart features in the home, including like this whole house sound system. And when we came in, there was really loud music playing over the system, and the agent who was showing us the house couldn't figure out how to turn it off, or at least turn it down. And it was really difficult to carry on a conversation. And neither of us wears hearing aids, but if we had, I know we wouldn't have wanted our hearing aids to go into some kind of music mode, even though the music was very dominant in that environment. So once we've established that we have a pretty accurate environmental classification, we can look at some features and what happens with those. And so let's talk about a practical application here. The headline feature when it comes to hearing and noise, and we talked about how important hearing and noise is to hearing aid users, is directionality. That's still like the go-to feature for helping people to hear better in noise, and it does work. There are some well-established limitations or downsides to directionality that can affect how people experience it and what their preferences might be. These include like own voice issues and changing sound quality because of the roll-off, but mainly, boy, I'm really frustrated with this presentation because okay, note to self, do not put animations on your slides because then your things won't show up. But anyway, that doesn't really matter. You know, there are downsides. The main downside that I want to mention here is that people get cut off from sounds around them. And it's really interesting that there's some data published quite a while ago by Mary Cord and colleagues, where they had people log where the location of the sound of interest was when they were actively listening to it. And they found that the assumption that the sound is always in front of the user, that the user is always going to be looking at what they want to hear, is not true about a third of the time. About a third of the time, people are actively listening to something that's off to the side, in back, or moving. You know, that could be like a conversation that's changing speakers, for example. So it's important for any sort of automatic system to take that, or a directionality system to take that into account, the fact that the user isn't always going to be looking at what they want to hear. So the GN strategy for applying directionality is trying to combine the strengths of technology with the strengths of the human. And you could compare this to like how a powered exoskeleton works. These are robotic machines that synchronize with the wearer's movement, and they give them added strength and support, but it doesn't take over what you do if you are wearing it. It enhances your intended natural motion. So you have the combined power of a person and a machine. And that's the idea of where we're going with the directionality. We want to support the way that people listen naturally, not take over and decide that you're only going to listen to what's in front of you. To do that, we have 3 listening modes. The names of them are kind of arbitrary, but the point is that each mode would be active in situations where people naturally tend to listen in a particular way. When the conditions are quiet or not very complex, we use spatial cues to form auditory objects and orient ourselves in the environment, and natural sound quality is important. So we want to make sure that we don't interfere with that. And as things become more complicated, the signal to noise ratio decreases, there's more non-speech sound, and we tend to naturally switch to a listening strategy that makes use of the ear that has the best signal to noise ratio for what we want to pay attention to. This is you could call this a better ear listening strategy. And there's no way that the hearing aids know what you want to pay attention to and what you don't. So they really shouldn't take over. There are situations where there is no intelligible or no detectable speech from the back, for example. In that case, we would have the hearing aids go full on directionality on both sides. That doesn't really happen very much of the use time because people, there tends to be, if people are in a speech environment, there tends to be some speech kind of all over the place coming from different directions. I would say probably 10% or less of the time we would be in this mode. We have quite a lot of literature on proof of concept testing this idea. We introduced it commercially probably 15 or more years ago, and we have had many iterations of it since. We're on our 7th generation. Again, we have no, stupid me, put an animation on the slide. We're on our 7th generation of directionality that provides directional benefit and still allows access to other sounds in the environment and supports different listening strategies. A technology that we've introduced in our latest iterations of that is based on 3-band binaural beamforming. And without going into a lot of details on this, we're splitting the sound up into bands and keeping the low band omnidirectional to avoid some of the sound quality and problems with directionality. And we only do, when I say binaural or bilateral beamforming, I mean using all 4 microphones on 2 hearing aids to form directionality, form strong directionality. This really improves the signal to noise ratio, but it also takes away binaural hearing cues. And some of those are preserved in the low frequencies because we keep them omnidirectional. And we also preserve some of the monaural spectral cues by limiting the high frequencies to a device-specific fixed directional response. So there's quite a few advantages to doing this in terms of the usability and the sound quality of the directionality. But how does it compare? There are some other devices on the market that use full band binaural directionality. If you've been following our story at all for the past few years, you will have seen us. I'm going to skip over to another slide that doesn't have animations on it, but you will have seen us claiming quite a large signal to noise ratio improvement in the situation where we have, let me see, I have a test set up here. We have a lady sitting here. She's listening to some speech in front of her, and she's got some competing noise coming from off to the side, but in the front. It's like at, I think, 70 degrees or something like that. but in the front hemifield. And that's not typically what you think of as where you get the directional benefit. We're always, in these tests, we're always putting the noise in the back rather than putting in the front. But with this technology, we were pretty interested in and confident in that this was so good and so sharp a directional beam that we would show a benefit, even if the noise and the target speech were co-located in the front of the person taking the test. And indeed, that was the case. We saw a directional benefit in this situation of over 8.5 dB, a little over that. And recently we thought, well, I wonder, there are some other hearing aids on the market that also have binaural beamforming, and all of the hearing aids on the market today have some sort of advanced processing. So we decided to, oh great, I don't have any animation here. We decided to compare, put other hearing aids into the same test situation and repeat it. So that first test we did with the product called ReSound Omnia. And that was the last generation, but still has the same technology as our newest product, which is called ReSound Nexia, or Beltone Serene if you were getting Beltone. And we replicated the same results here in the first column with 7.8 dB directional benefit. So that was, and it was not significantly different than in the earlier study. So that was great to see. It was really impressive and surprising to me to see that across all the other hearing aids that we tested, that they also did provide directional benefit in that sound setup. So none of them went to like a cardioid or something that would not suppress any sound from the sides. So that was really encouraging or interesting to see. But we also saw that our technology seems to be even better at doing so than other hearing aids on the market currently. Finally, as much as I would have loved to talk about directional technology all day, we need to tie this back into the environmental classification. And I had picked directionality to talk a little bit about just because it's for sure the one feature that every hearing aid brand turns on and off automatically based on some kind of environmental analysis. And of course, it's the industry's main answer to problems hearing and noise. In fact, I think directionality was the first feature that was incorporated into an automatic switching algorithm. Now, remember I showed you how the environmental classifier divides up the world into prototypical environments on the basis of signal to noise ratio and overall sound level. Well, if I told you after all of this that we really don't use this to control the directionality or the noise reduction or the wind noise reduction or other features, you would say, well, why have we been talking about this for an hour? In fact, the only features that are explicitly controlled by that environmental classifier, as I presented it to you with the signal to noise ratio against with the 7 environments and those 2 axes, are features that are called in ReSound Environmental Optimizer and Environmental Optimizer 2, and in Beltone they're called SmartGain and SmartGain Pro. And we also use it explicitly to control the automatic volume for the tinnitus sound generator. So now you're thinking, well, what's the point of this class? In fact, what a classification system like this is quite rigid, really, and it doesn't do enough. It's not nuanced enough to tell us everything we need to know about what's going on acoustically to control a feature in real time optimally. But all of the same information that's used in the categorical classification system is also used on a continuum to apply and steer all of these sound processing features, sometimes along with extra information that we can pull out, as is the case with directionality. We talked about how we identify speech, for example, but while the classification system is only concerned with whether there's speech, is there speech or isn't there speech, in order to place the listening situation into a category, it would be helpful for controlling the microphone modes to know where the speech is coming from and deciding how to control the microphone modes to support the user's natural listening strategies. So on each hearing aid, we'll have a speech detector that faces front and one that faces back. So we can break down speech as where's it coming from? The left, the right, front, back, everywhere. By having this extra information about direction of arrival, we combine with the other information from the environmental classification system that we already talked about, in addition, those input levels, noise levels, and the decision algorithm can then figure out which microphone mode to apply that balances directional benefit with access to surroundings, or whether we should go full on directional, or whether we should be prioritizing spatial cues to best support the hearing aid wearer. As another example related to directionality, we have a feature for monaural fittings and also in lower technology level devices that also decides about turning on directional microphones or not. That's called soft switching in ReSound hearing aids and SpeechSpotter Pro in Bell Tone hearing aids. And again, we use the speech detectors that are looking in different directions to help make decisions about that, in addition to the other information that feeds into the categorical classification. So the environmental classifier, if you're only thinking about it in terms of the categories, those 7 categories, it's a window into how the hearing aids are breaking down the acoustic environments. And because we show it to you in data logging, you can get a general idea of what sorts of environments your patients are spending time in when they're wearing their hearing aids. And we can also use it in a non-clinical way, as I showed here, to check accuracy of environmental analysis compared to human judgments. So we get a better idea of whether the hearing aids are going to be doing what we want them to do when we want them to do it. As I showed you, the speech detectors in our system seem to be a differentiator compared to other hearing aid brands because of the differences in agreement with subjective evaluation of speech and noise environments. But the biggest difference in the environmental analysis across different hearing aid manufacturers seems to be that we've decided not to use any automatic steering based on music identification. So apart from the fact that music is present in many daily environments and there's not really a way for us to know whether to enhance it or not, you may also have triggers for music identification that are false positives. They're just wrong, as in the vacuuming example, that could ironically lead to hearing aids doing exactly the opposite of what the hearing aid user might prefer. So to sum up, today's hearing aids apply automatic algorithms to control different hearing aid features, including directionality. The action of those algorithms is based on analysis of the acoustic environment that's carried out by the hearing aids. So it's important that the environmental classification or analysis is as accurate as possible so that the hearing aids don't apply settings that interfere with the hearing aid user's listening intent. And we showed back in 2017 that the environmental classifiers often were inaccurate in complex listening environments, and that music identification seemed to be responsible for much of the inaccuracy. In an updated investigation last year, I guess it was, with current hearing aids, we showed that GN continues to have the most accurate environmental classification. And the rationale for using the environmental classifier data to control the hearing aids is also critical. Our philosophy aims to empower the hearing aid user to control their listening experience rather than empowering the hearing aids to make decisions about what sounds are relevant for the user. So that's what you do with the information from the environmental analysis is just as important as the information itself. With those words, I don't know if we have a minute for questions or comments, but otherwise, thank you so much again for being with us today.
Thank you so much, Jenny. That was amazing. That was such a brilliant overview. I particularly found it interesting hearing more about how we make the environmental classifier so accurate with the speech detector and everything. That was very cool. And I feel like you left a little bit of a teaser. I feel like we need to get you back now to talk more about directionality another day as well. So we are out of time. So I just want to make sure that everyone's aware of how to get those very, very important CPD points. So if you are collecting points through Audiology Australia or COD, this session has been endorsed. So there, after the webinar finishes, you're going to get a little email sent out, which will give you a link to a survey and a quiz. And if you can complete that, then we'll send you CPD certificates and get you your endorsed points. If you do have any questions, then please send them through to the ANZ team, and then we'll link in with Jenny to get any questions answered. But thank you so much for joining, and everyone enjoy your day. And thanks again, Jenny.
Thank you.